Hey folks, this is the first video in a multi-part series of short videos leading to the concept of the tensor product in linear algebra. Well, I suppose technically the first video is the intro video I made before this one covering why I created the series and why I may have anger management problems. You can watch that video if you want to. You can also just keep watching this one. In this video, we're going to cover the quotient vector space from a universal point of view. I'm assuming you've seen vector spaces and linear maps before. I'm also assuming you've probably seen the quotient space before, since it's covered in many introductory linear algebra courses. But in this video, we're going to focus on its universal property, which will better prepare us to understand the tensor product later. Let's get started. Let V and W be vector spaces over a field F, and let phi be a linear map from V to W. Since phi is linear, it respects linear relations. That means the linear structure in V is reflected in the image of phi within W. For example, the linear relation among vectors in V on the left here is mapped to the corresponding linear relation among the image vectors on the right. This is just from the definition of linearity. But the map phi may also impose new, compatible linear relations in its image. As an extreme example, the zero map imposes that each vector becomes equal to 0. To describe this in more violent terms, we say that the zero map kills V. Of course, nothing is changing in V itself. This is all happening in the image of phi, but intuitively it can be convenient to think and talk of these relations as being imposed in V in order to obtain the image. More generally, let S be a subset of V, which is not assumed to be a subspace. If S is contained in the kernel of phi, then by definition of the kernel, phi kills S. Since phi is linear, it follows that phi actually kills the entire subspace K spanned by S. In other words, phi imposes that all the vectors in K become 0. A question we can ask is there a universal linear map that kills K, from which all other linear maps that kill K can be obtained in a natural way? If so, it seems like it would be worthwhile for us to find it, because by doing so, we would fully understand what it means to kill K, and hence what it means to impose relations making the vectors in S become 0. Let's explore more precisely what such a universal map would even be. First of all, it would be a linear map, let's call it pi, from V to some vector space Q over F, with K contained in its kernel since it kills K. And we should be able to obtain any other linear map that kills K from this map pi. A way to express this precisely is that for any linear map phi from V to any vector space W over F with K contained in its kernel, there should be another linear map, let's call it phi bar, from Q to W, which allows us to obtain phi from pi through composition. Here's what that looks like in a diagram, which is easier to understand. The arrows represent the linear maps, and we can see how they compose visually. The diagram is said to commute because going right and then going down has the same effect as going across diagonally. This captures what it means for phi to be obtained from pi by way of phi bar. However, there's another important detail to express. Recall we wanted to be able to obtain phi in a natural way from pi. This requires that phi bar should be uniquely determined by phi. Otherwise, we might have to make certain arbitrary choices to determine phi bar, which intuitively isn't natural. With this detail in place, we now have a precise mathematical description of what it means to be a universal linear map killing K. This is called a universal property. The burning question is there such a map pi? You may have already guessed the answer. Yes, there is. We can take pi to be the canonical projection onto the quotient space V mod K. It satisfies the universal property on the previous slide. Writing V bar for the projection of the vector V, we have that phi bar of V bar equals phi of V, which is convenient notationally. Importantly, phi bar is well defined because phi kills K. Notice that this universal property allows us to factor out the part of phi that kills K into pi. Pi kills K and does nothing more, while everything else that phi does is carried out by phi bar. For this reason, we say that phi factors through pi. So the universal property says that every linear map that kills K factors uniquely through pi. If you've seen the quotient space before, you'll recall that it consists of the cosets of K in V, where the projection of X is just the coset of K containing X, and addition and scalar multiplication are defined so that projection is linear. If you haven't seen the quotient space before, well, now you have. You can verify that addition and scalar multiplication are well defined and make V mod k into a vector space, and that projection is linear with kernel k. However, a major point I want to convey in this video is that from the universal point of view, these implementation details of the quotient space are not really important. They show us that a universal object really does exist, so they serve a purpose, but beyond that, everything we need from the quotient space we can get from its universal property. It's helpful to think of the universal property like the user interface of an app, but instead of containing buttons and sliders, the interface contains objects and arrows, namely vector spaces and linear maps satisfying certain properties. As long as the app works, you don't usually care about its implementation details, and the same is true here. To illustrate this, and to get some practice using the universal property, let's suppose that rho, from V to some other vector space R over F, is another universal linear map killing k. Then, by the universal properties of pi and rho, there exist linear maps rho bar and pi bar, making this diagram commute. Here we have pi on top and rho on bottom, although they like to think of themselves as versatile. The vertical line on the left is just the identity map. Rho bar on the right going down exists from the universal property of pi, allowing us to obtain rho from pi. Pi bar going up exists from the universal property of rho, allowing us to obtain pi from rho. Now, reading this diagram, we see that pi bar after rho bar after pi is just pi. That's because rho bar after pi is rho, and pi bar after rho is pi. You should pause the video to confirm that you see this. Dually, rho bar after pi bar after rho is just rho. Again, pause to confirm. Translating these equations into diagrams, we see that these two diagrams commute. These say the exact same thing as the equations. Let's focus on the diagram at left and think about the universal property of pi. Recall the universal property of pi says that any linear map that kills k factors uniquely through pi. Here pi is factored through itself by way of the composite pi bar after rho bar. But trivially, pi also factors through itself by way of the identity map. That is, in this diagram, we could replace the vertical arrow with the identity map on V mod k, and the resulting diagram would still commute. By the uniqueness requirement in the universal property of pi, that means that pi bar after rho bar is the identity map on V mod k. By the same reasoning applied to the diagram at right, rho bar after pi bar is the identity map on R. So rho bar and pi bar are mutually inverse. That means we have an isomorphism between the universal maps pi and rho, as seen here. Since rho was arbitrary, this shows that the quotient construction is unique up to isomorphism. Intuitively, anything that satisfies the universal property for killing k will be essentially the same as the canonical projection onto the quotient space V mod k. Using our prior analogy, we can say that although its internal implementation details may differ, it will be an app with identical functionality. Similar reasoning can be used to show that any universal object is unique up to isomorphism. In summary, we've seen in this video that the quotient construction is the universal way to impose new relations in a vector space, namely by killing off a subspace. We've also seen that everything we need from the quotient construction we can get from its universal property. Hopefully this has gotten you more comfortable both with quotient spaces and with universal properties. If so, let me know in the comments. In the next video, we'll examine another important universal object, taking us one step closer to the tensor product.